Welcome to this sixth session of the Ham Radio Extra Class License course. Our first subject will be radio signals and measurements. Let's start out by refreshing our memory on AC waveforms and measurements. The sine wave is the single most fundamental of all waveforms. It consists of energy at a single frequency. The equation for the amplitude of the sine wave is A equals sine of the quantity 360 times F in hertz times T in seconds. Given that the peak of a 60 hertz sine wave is 1 volt, what is the amplitude at T equals 1 millisecond? Well, using our formula A equals sine of the quantity 360 times F times T, when we substitute the values, A is equal to sine of the quantity 360 times 60 times 0.001, which equals 0.368 volts. In what we call the time domain, we are looking at how the amplitude of the sine waves varies with time. A graph showing all the frequency components of a waveform by frequency and amplitude is called the frequency domain or spectrum. Here we see the spectrum of a pure sine wave. Notice that there is only one vertical line showing both amplitude and frequency. Here is an example of a complex waveform made up of 3 sine waves, all at different frequencies. Here is what the spectrum of that signal would look like. Notice the 3 frequency components and the amplitude of each. On the right, you can see an example of a sawtooth waveform. The spectrum plot of this waveform shows that it is made up of a sine wave and all of its harmonics. A square wave is made up of sine waves at all of the odd harmonic frequencies. Notice that there are no components at 2, 4, 6, etc. times the fundamental frequency. There are also pulse waveforms. Notice the waveforms for pulse position modulation, pulse amplitude modulation, and pulse width modulation. An example of a radar pulse is shown at the bottom. Let's refresh our memory about sine waves. There's volts RMS, there's volts peak, and there are volts peak to peak. Here we compare the measurements of a sine wave and a square wave. You can see how volts RMS, peak volts, and peak to peak volts compare between the sine wave and the square wave. What is the RMS value of a sine wave with a 10-volt peak? Well, volts RMS equals 0.707 times the peak voltage, which equals 0.707 times 10 volts, which is 7.07 volts. What is the peak-to-peak value of a sine wave with an RMS value of 65 volts? To get voltage peak to peak, we first need to know voltage peak, which is volts RMS divided by 0.707, which equals 1.414 times the volts RMS, which equals 91.9 volts. Now the volts peak to peak will be twice the peak voltage, which is 2 times 91.9 or 184 volts. What is the peak-to-peak value of a sine wave with an RMS value of 120 volts? Well, to get the peak voltage, we multiply the RMS voltage by 1.414, which gives us 170 volts. Then, to get the peak-to-peak voltage, we double the peak voltage, which gives us 340 volts. What is the RMS value of 380 volts peak-to-peak sine wave? We start by calculating the peak voltage, which is 0.5 of the peak-to-peak voltage, which is 170 volts. To get the RMS value, we multiply the peak value by 0.707, which gives us 120 volts peak. What would be the most accurate way of measuring the RMS voltage of a complex waveform? Answer A, by using a grid dip meter, B, by measuring the voltage with a D'Arson voltmeter, C, by using an absorption wave meter, or D, by measuring the heating effect in a known resistor. The answer is D, by measuring the heating effect in a known resistor. What type of wave is made up of sine waves of a given fundamental frequency plus all its harmonics? A sawtooth wave, B, a square wave, C, a sine wave, or D, a cosine wave? The answer is A, a sawtooth wave. And now let's take a look at RF power measurement. Power average in a sine wave equals RMS voltage times RMS current. Peak power equals 2 times the average power, which equals the peak voltage times the peak current. And average power equals the RMS voltage squared divided by impedance. What is the average power during one cycle in a 50 ohm load with a RMS voltage of 70 volts? Well, average power equals voltage RMS squared divided by impedance, which equals 70 squared divided by 50, which equals 98 watts. What is the average power during one cycle in a 50 ohm load with a peak voltage of 35 volts? Well, volts RMS equals peak volts times 0.707, which is 24.7 volts. Average power equals RMS voltage squared over impedance, which equals 12.2 watts. Peak envelope power, that is PEP, equals power averaged over one complete cycle having the greatest amplitude. Typically, peak envelope power is 2.5 times the average power. This is true for a voice modulated signal. As we said, peak envelope power, PEP, equals power averaged over one complete cycle having the greatest amplitude. Peak envelope power equals RMS voltage squared divided by the load resistance, which equals peak envelope power times 0.707 quantity squared divided by load resistance. What is the peak envelope power of a transmitter with a peak envelope voltage of 100 volts across a 50 ohm load? Well, we said that peak envelope power equals 100 times 0.707 quantity squared divided by 50 for this problem, which equals 100 watts. What is the peak envelope power of a transmitter with a peak envelope voltage of 30 volts across a 50 ohm load? Well, for this problem, peak envelope power equals 30 times 0.707 quantity squared divided by 50, which equals 9 watts.